research field that's quite new that asks the questions, what happens if we put quantum computers into the mix of hardware? What if we put quantum algorithms into the mix of software algorithms? What does it mean for machine learning? Does it increase the way we can learn things? What generalization power do models have that we build from quantum mechanics, and so on and so forth? And I'll go over a quick recap, and then I'll just basically finish that section from yesterday. That's the goal for today, and I think we've got a long question and answer session after that. So I kind of motivated the whole talk by saying that quantum computing research has a bit of an interesting split recently between like good old quantum computing, which is like kind of the theoretical ideas of like pinpointing a model of a quantum computer that might one day be possible or not, and inventing algorithms, analyze them very theoretically, like computational complexity wise. And kind of since a couple of years, we've got actually prototypes of these quantum computers, and now things change. How we do research, a big influx of money, power, IT companies, industry. So there's also cultural change. But we really have now a lot of drive to find applications that can be implemented on those prototypes already. So these are always the two like angles you have on anything that is in quantum computing research at the moment, and also on quantum machine learning. And quantum machine learning over the last year, so it's not a term that refers to like a single thing, but I hope it got apparent that there's actually a whole landscape of ideas that people have contributed. And I like to kind of like distribute them to the three pillars of kind of the definition of machine intelligence, which would be like, you could think of data and distributions. You could, for example, think of data being given by a quantum system. For example, a photon could carry a certain amount of information, and then you can think about, so this is in quantum physics a probabilistic system, and you could think of what actually can we say about learnability of those systems if we can act on them in some ways. Then the second step was kind of like about hardware and algorithms, where people have thought like, let's just take machine learning algorithms, like let's identify, for example, if there's a matrix inversion problem behind optimization in this machine learning method. And then let's see if we can speed it up with a quantum computer. So this is kind of like part of more the old school research in quantum computing. And then what we spoke about, and I'm actually happy that I started with that one, is my favorite field of research at the moment, which is what happens if we turn our quantum hardware into models? So what happens if we kind of interpret, feeding inputs into them and interpret the measurement results as predictions, for example, and think about it as a supervised learning classifier. And so I won't get to these two blocks here. It wasn't like really very, I just wanted to give you like basically an idea of those ones. You have to go and read up on them yourselves, but I will kind of just conclude this idea of models. And what I promise to do is to tell you in a little bit of a deeper way, how do these models that are now given rise to by quantum computers, they're not like magic. They are also like just mathematical structures we can write down, and we can look at the maths and think about how do they resemble neural networks, how do they resemble kernel methods. And so I'm just picking out those two because there was a lot of work on those. And so this is what I want to conclude basically now. And just for those of you who like code, I'll just show this again. So the idea here is really, and software does this already in this fashion, that I take a machine learning algorithm where I have like somewhere a block that is a model, but the optimizer is classical, the loss is classical, everything is classical. So I just have a black box model basically, and I replace this now with quantum hardware. And so here, this was an example from one of the quantum machine learning frameworks called Penny Lane. And you see that it really looks exactly the same, except from one part has this strange circuit and expectation values and like a little bit of a different notation. Okay, cool. And then I spent quite a lot of time in trying to tell you about the mathematical structure of quantum computing. And here also just a quick recap. Most of quantum computing, most of the papers, most of the research think about a qubit model in which a quantum computer is nothing else than n systems that can be in two states each, so zeros and ones. So these are our quantum bits. They're in some sense nothing else than classical bits. So a lot of the magic that people always think is in quantum computing, the collapse of the wave function or superpositions, actually have a very clear classical analog. They are just basically another way to describe probability theory. So what quantum theory tells us about the system is basically the probability of measuring the system in a certain state. So classical computer would kind of give you an output, which is a bit string, a quantum computer would give you an output which is a bit string sampled from a distribution. So basically this distribution is in some sense the output of the quantum computer. And so a distribution, probability distribution over n binary variables, you can describe by a 2 to the n dimensional vector. And then I kind of try to develop these like pictures here on the right side, where this like rectangular box is kind of this 2 to the n dimensional vector. And I told you that the entries here are not like in probabilities positive and real, but they're actually complex and they can also be negative. This has then gives rise to like effects like interference and entanglement. And this is why we don't talk, for example, about correlations where we talk about entanglement. We don't talk about uncertainty, but we talk about superposition. So because this object here really looks a bit different, the maths of probability theory is a bit different. Again, how to interpret this thing is if you look at the entries, every dimension, this just convention refers to one of the possible measurement outcomes. So basically one of the binary strings you can read out of your quantum computer. And you have to take the absolute value squared of this complex number, and this gives you the probability of this event to happen. So this is a bookkeeping vector of your probability distribution. This is obviously a vector that's like in probabilistic machine learning, it's too large to even write down in many realistic cases. And so this is basically just the mathematical framework that describes quantum physics. And kind of the largeness of this vector is exactly the reason why we are stuck with either very small scale simulations, because we can only write down this vector for like, maybe 15 qubit systems, 20 qubit systems. With a lot of tricks, we can push it probably up to 50 qubit systems or something like that. But after that, we're completely lost and we need the hardware. And the hardware is kind of noisy, it's small, it's not entirely developed yet, it's more like prototypes. So everything we talk about in quantum machine learning is really like, either you have to theoretically investigate it, or you have to make small simulations, or you have to make very noisy real life simulations. So you're a bit like in a rut where, which explains maybe why we can't really say yet a lot about this is like much better than classical algorithms, for example, something like that. Anyways, so this bookkeeping vector here, which is called the quantum state, what an algorithm does, so this is kind of like here the timeline, what an algorithm does is basically just a unitary, which is just a certain type of linear transformation of this initial state. So, and since a quantum algorithm, like classical algorithms on the elementary level, consists of lots of little gates, this is the same case here, you can actually write down a quantum algorithm as kind of a chain of these linear operations. And then to get out, so in the end, you get kind of a distribution you can sample from, but to get actually an expectation value, so a measurement average, you would kind of have to build this quadratic form here. And this is something that's, mathematical expression that you find all over quantum theory. So this is like the format of an expectation value for an n qubit system. Okay, and then there were two like kind of hints towards like what's coming now. Is the first one is quantum gates can be trainable, and this sounds super trivial, but it took actually many years to like understand. So people always found this trainability, or this that you can vary gates. They wanted to get rid of this, so they wanted to basically implement this perfect gate that we said this is the building block of a quantum algorithm. And only because these near-term devices came up, people have asked basically what can we do with those devices, because we can't really like determine the parameters like with a super high precision. So what they said, let's just use these physical parameters, don't fix them, but actually like use them to vary them. And now we've got these variational algorithms that we can kind of train these quantum computers. And the second ingredient was, it's also more an insight that sounds very obvious, but that took a while, is that the moment you kind of encode data into your physical operations, so you kind of shine a laser light or have an electromagnetic field that depends on X on an input, what you effectively do, you kind of embed this input into a 2 to the n dimensional feature vector. So you automatically do that. Just hearing, is there anything? Okay, cool. Great. Okay, and then the last thing that I said is, okay, the first, before I even ask what are the models that we implement here, we have to actually say that this is practicable, and it's practical only if we can get gradients out of our quantum algorithm. And they said there's a lot of research at the moment based on this very beautiful result that you can compute, or you can estimate an analytic gradient, so an exact gradient on a quantum computer, by doing something that looks like finite differences. You run your quantum algorithm twice and you shift a parameter to the left and to the right. But you shift it by a macroscopic parameter, which is super important, because if it was microscopic, it will be very hard to implement on our noisy devices at the moment. Cool. And then lastly, I'm kind of left with the section of like really explaining what are these models now? Like what, so I won't go as deep as saying like what can interference do, but the structure of a unitary evolution, what can we do with this? So, and I have to say about this also, like a lot of students, especially in this field, they are almost blue-eyed themselves in that they always think like quantum has to be more powerful in some sense. So they very often just think, they don't even ask what's the maths behind this, which could be really, really stupid maths, right? It could be a really, really stupid model that doesn't learn anything. But they just automatically think, because we imagine or we think that quantum computers are more powerful in a very general fashion, that now these machine learning models have to be better as well. And this is definitely not established yet. And it's hard to establish at the moment, to be honest. Okay, cool. So let's make the link to neural networks first. So in my kind of block language here, this would be how a neural network looks like. You take an input and you have these like linear transformations chained by these element-wise and nonlinear transformations. And now let's look at the block notation of a quantum circuit where I don't do the measurement now. I just basically prepare a quantum state and then I'll stop for now. So my quantum state is still in my quantum computer, so to speak. And I could now sample from it, for example. And you see here, I kind of like have this first operation that encodes data into this really high dimensional vector that represents this quasi probability distribution. And then I've got these like linear blocks acting on it. So this is why you can immediately say that quantum circuits are unitary neural networks in feature space. And there are a lot of interesting parts about this. So, I mean, obviously, unitary means linear. So these are the vanilla quantum circuits will always be linear neural networks in feature space. And we all know that neural networks really depend on their nonlinearities to work. There's a lot of work, and I've done a lot of this at the beginning of my career as well, about trying to get nonlinearities into here. But this is hard because, you know, you can do this with measurements, with tricks, but you always pay a price. Like you always decrease the chance of measuring the right result, or there's always like these kind of like bounds. It's almost like nature doesn't want this to happen. And it makes sense because probability theory is kind of, in some sense, a linear theory, right? And so, but why is this still interesting? The first way we can think about this is, what does this unitary structure do? So I already like said, in training, we figured out that this unitary structure gives us some problems. So it's slightly different. There also, in classical literature, there was a couple of papers on unitary recurrent neural networks, for example, that say like vanishing gradient problems can be mitigated by unitary weight layers. So maybe we can get something out of this unitary part of it. But also like the kind of interpreting it as a deep linear neural network is at least interesting on a theoretical basis, because now you can go and say, if this block here, if this matrix here represents a quantum gate or the action of a quantum gate, and we represent matrices always as connections between neurons, then you can ask, what connectivity structure does a quantum gate correspond to? And so for the, it's a bit like pixely here, but so for example, this is, for example, the connectivity structure of a specific gate, this one of another specific gate, of a very typical local gate that people use all the time. Now, how many qubits are in the system? I guess it's like probably 32 dimensions here. So these are all, this is your basically your dimensions of your probability distribution. So if we have 32 dimensions, we've got five qubits. I don't know. I would have to think about this. But so just interpret this here as the quantum state, basically. And now I make an operation on the quantum state that's characterized by the matrix, which corresponds to this connectivity. And you see, this is a highly structured connectivity structure. So we can also say that quantum circuits are unitary, highly symmetric neural networks in feature space. Cool. I would say that 80% of all people in quantum machine learning who do this near-term stuff at the moment think only about neural networks, maybe even 90%. I personally am completely against that. So this is now like a bit of a preference that I will tell you. I think that it's kind of, this is for me where it ends. Okay, what can we do now with this? And the interesting part for me is the feature space part, because I find that quantum circuits really resemble a lot more a different model, which would be like a support vector machine model. And maybe you see this now as well. So just as a quick recap, I know that kernel methods are not so famous anymore at the moment, but you probably have the basics. I find them extremely beautiful because they have such a beautiful like theory that reminds me a lot on quantum theory. So ideas, there's always this picture of like you have an input space of data, you've got a feature map, and then you've got a feature space. And usually this feature space is infinite dimensional or very, very high dimensional. You never really compute in this feature space. So this is, again, like exactly like in quantum physics, this is just a mathematical construction here. And now, to summarize really, really roughly, there are kind of two objects here that are interesting for us. The first one is a distance measure between inputs. So something called kernel, a positive definite like function. And it turns out that a distance measure on the input space is always related to a feature space where you can just take the inner product of the corresponding feature vectors. And then there's another like object, and they are like very obviously there are close ties between these two like expressions, but I think it's almost like two didactic schools of how you can explain like kernel methods. The second idea or the second notion is that you can interpret like a model, like just like a classifier or something, as a linear model in feature space. So you kind of map your inputs with a feature map, and then you take an inner product with some other state or some other vector in your feature space. And this is kind of like a very powerful linear model. And this is often like in textbooks, this is how you find kernel methods introduced, that you just say, okay, we take a linear model and make it more powerful, put a nonlinearity in this feature map, and then do things linear. And now it turns out that on a quantum computer, both angles are super interesting, because the first angle here is interesting because I just told you that encoding data into a physical state is a feature map. And it turns out that we can actually take inner products of quantum states quite easily. So there's a very simple algorithm, near-term devices, you can implement them. So we can get actually the inner products in this feature space. So we can already kind of implement an SVM, a support vector machine, with a kernel, where the kernel acts really in the Hilbert space of a quantum system. And now the second one is also interesting because this is kind of in some sense exactly what we do in a quantum algorithm. Let me try to give you an idea. So in a quantum algorithm, you map an input to kind of this like quantum state, which is high dimensional state. And now this was a measurement. Sorry. And now I have to give you like this little clue that there are measurements that you can express as this object here, which is just W is here now a vector also in the same space that like phi is from. So it's another quantum state, so to speak. And you just have this outer product. And if you now execute this, you find this form here, and this is, looks very similar, except from that everything is complex. So you have like kind of this like dagger here, and then you have this absolute square that we always get out of measurements in quantum theory. But this kind of looks very much like a linear model in feature space, right? So I would say not even in quantum machine learning, that I would almost be a bit radical and say every quantum computation is some kind of support vector machine type model. So obviously you would have to optimize in a certain way to like maximize margins and stuff like that, but the theories are very, very closely related. I'll just check time. And so if you don't like maths, you can also just explain it in pictures. You remember this like Bloch sphere was this idea to represent a quantum state before. And let's say now you have an algorithm that kind of picks, so you for example, you shine a laser light onto qubits or onto like a superconducting circuit system or whatever. And you shine the light as strong as a pixel is dark or something like that. What does that mean? After you have kind of like embedded all your pixels into like your physical state of your system, your physical system is in some state in this like space here, which is like this quantum Hilbert space. And you can do this for other data points. And if you have a feature map, so an encoding strategy that is really clever or that kind of manages to separate your data, so where the nonlinearity is kind of like class separating, then you can now just with a measurement determine kind of what's the decision boundary between the two. And why this is super interesting is that quantum measurement theory and how to distinguish between two ensembles of quantum states is very old and very well understood. And it's actually quite beautiful how you can connect this like deep old quantum information theory now with machine learning in quite a nice way. Just to give you an idea, because I know this is a bit cryptic at some stage, but so the easiest quantum feature map, so like encoding data into a quantum computer, will be, for example, the following. Let's say you have an input that's just a binary string of 3 bits, and what you want to input is x equals 1, 0, 1. And now you could just do a quantum circuit that looks like this, and the x in this quantum circuit just stands for you flip the qubit. So when you start in 0, 0, 0, what you have at the end is a quantum state that's totally deterministic in the state 1, 0, 1. And what feature vector or what kind of like quantum state does this correspond to? You remember if a state is deterministic, I just have a 1 somewhere and 0 somewhere else. So it would be like a computational basis state here. And so what does that mean? I have my feature map literally maps all inputs to another standard basis vector in a really high dimensional space, which is not a very interesting feature map, or maybe, I mean, it will be something that's completely overfitting. The space is much too large. Like if you learn on data, you can never like really like fit your test data out of like various reasons, but it's still like quite interesting that anything you do kind of does something like a mapping like this. Okay, I'll skip over those. Just as a little hint, obviously, we're kind of guilty of the same stuff in machine learning. The moment you've got a model, you want to train it somehow. And obviously, there was also a couple of ideas on how to train these feature maps, because it's quite hard now to say, like, this quantum circuit maps your AND pictures to the side of your space and the B pictures to the other. And yeah, you can run these little experiments. Let me just show you this one, for example, where you literally have image data. So this is, for example, now done in the Penny Lane framework, where you can have these big quantum and classical machine learning pipelines together. So you take a ResNet, you chop off the last layer, you kind of connect it to, or you kind of connect it to a new layer that reduces your data to 2 dimensions, but you haven't trained it yet, so that's why it's red here. And now you feed these 2 values that you get out of this whole process into a quantum circuit, and the quantum circuit has these red parameters that you can also train. And now in the end, you get a quantum state somehow out. And now you can train the entire thing to separate images of B's and Ands, basically to be in different parts of your Hilbert space. And can also like look at what's the representation that the model learns. So for example, if blue and red are the different classes you want to learn, you really see that it separates it in a very, very periodic manner somehow. So the quantum circuit seems to like this kind of like embedding, this intermediate step where the data is separated in this periodic grid. And basically, lastly, I'm actually super happy about this, because this only came up on the archive this morning, and it's a paper that me and 2 of my colleagues were working on really, really hard for a couple of months. And it kind of explains a little bit this result of like, why should the quantum model, or why, if I train the entire pipeline together, why does the classical model learn to kind of arrange the data periodically? And it turns out that, in a few words, that a quantum circuit or a quantum model can be quite nicely described by something that you would call a partial Fourier series. So assume most of you know what a Fourier series is. A partial Fourier series would just be a Fourier series where you don't have the entire frequency spectrum. So your frequency spectrum is usually all integers up to infinity, and any function can be expressed by a Fourier series. So it's a bit like a Taylor series. But it turns out like a quantum model has, or most quantum models have, a limited spectrum of this Fourier series. And the second observation, if this is not already like buzzing your head a bit, is that actually how many frequencies you have in your series completely depends on how you embed your data. So we have a clear link here between the feature embedding strategy, or the feature map that a quantum computer implements, and the expressivity of a model in terms of how many Fourier frequencies can it support. And the rest of your circuit, like, so in this case, like here, I draw a circuit where I do something, then I embed my data, then I do something, then I embed my data again. You can do this like over and over again. So the rest of all this circuit kind of determines what Fourier coefficients you have. And you can now really play this game of plotting, and can say, okay, this quantum model here, I don't know if you can read this already, but for me, this is like something happens, some operation happens, then I encode my X, then some other operation happens on a single qubit. And I try to fit a Fourier series. So I have a ground truth now that's also a Fourier series of degree 5. And the quantum model, this is after training, the plots you see here, cannot fit the Fourier series of degree 5 here, because it can just like, fit just a very, very simple sine function. And now if you increase kind of your embedding layers, in the sense, you can fit higher and higher orders until if you have 5 of those layers, you can exactly fit a Fourier series of degree 5. And the same happens if you kind of repeat your embedding over qubits, so not just in layers. Okay, cool. I know this was already, even for quantum machinery, this would be a bit advanced, but just to summarize out of this, when we think about what our, when we think about what quantum models actually are like, we don't have to be blinded by the fact that there's something happening that's kind of non-classical here. we just have to look at the maths, and the math says, quantum models look a bit like linear neural networks in very high dimensional spaces. You can push in some nonlinearities if you want, but much more general or much more natural is this approach to say a quantum computation is kind of a feature map plus a linear model plus this like square factor that you always saw. And then we can ask what feature maps can quantum computers actually generate, which is already a smaller question than what quantum models can we have, right? And then this last part should tell you that actually, and not surprisingly probably, because there's this wave nature, they're like imaginary numbers, like everything sounds like waves. It seems like quantum models very naturally express the class of functions that are Fourier series of different degrees or various degrees and frequency spectra. Okay, cool. Then I'll skip through the slides, everything that we're going to do today. And just, yeah, and I hope you also like got from this like very short 2 lectures that this quantum machine learning thing, it's a very interesting field, but it has tons of open questions. So we haven't answered the question, is this actually even interesting to do machine learning? So this is really, if you are keen to do something that is really explorative, that not everyone else is doing, that's kind of very physical, very scientific, and where we just doing the first steps of understanding what we actually have in our hands, where you can also play around with hardware that's growing and growing. Yeah, then try it out and drop me an email. I think you find my email address like online everywhere if you've got questions about this. And some of the open questions here are, as I said, like what models are quantum circuits? I try to talk about this a bit. Are they actually useful? Do they perform well when we increase the problem size? At the moment, we test everything with very small data sets. What do these noisy devices do for the models? Are there domains that they're good for? So if we've got these Fourier structures, maybe signal processing is the right idea. And so on and so forth. Great. Okay. I think that's it. And I think.
Yes, I'm here, and we have already quite some questions from the audience for you, Maria. And so in general, so the first one is, so at the moment, where is the field at? Is it more about creating the tools and the ideas for the moment when quantum computers appear, or are there already applications or specific use cases that have been shown success?
Yeah. So I think this question will be answered differently if you now talk about quantum machine learning from more, as I said, the theoretical old school perspective or the near term. So I assume that you talk about the near term one. And they're definitely, I think when you listen to the news and see like all these beautiful articles in the tech magazines about quantum machinery, you might think that we're already at the brink of having an application and running those things. And maybe in 5 years' time, all the big companies wish they had invested earlier and stuff like that. I think this is definitely not the case. I think what happened is the following. People have started to explore quantum machine learning a couple of years ago, and then they hope that there will be an immediate result. For example, our hopes were actually, we can immediately show that there's an exponential speed up if you do quantum computing for machine learning. This hasn't happened. It has all turned out to be a lot more complicated, as always in science. I mean, any good science is much more complicated than just these simple answers. And I think now people in the last years have taken a step back and start to really go back into theory and start saying, okay, these machines are not ready yet to run our stuff. So let's just explore the problem theoretically for now. And when you have this step back and go into theory, and good theory work takes many, many years, I would say that we're talking about horizons that are more in the 10 years or 20 years until there's an application that works for. And also, we don't know, so the difference between the big quantum computer we're trying to get one day and these devices that are there today is error correction. So these devices are not error corrected, and every computer that you work with is error corrected. And there's a couple of physical principles that are a problem for quantum error correction, but there's obviously a lot of theory, but it's a lot harder to solve this problem. So it's not just these devices grow, but there's actually something that has to change in them. And so we don't know if any industrial scale application will be there for the small scale devices. We think there will be some for the bigger quantum computers, but that will take a longer time for engineering. That was a complicated answer for a simple question.
And with that in mind, has there been any breakthrough in quantum machine learning? So in regarding applications or theory in general?
No, I think it's more step by step we're understanding more and more things. So in my mind, there have been a couple of papers that were kind of breakthrough in terms of that they make us understand how we have to think about the problem. But in terms of like now that someone demonstrated that something crazy happens, I think the answer is no. And I would also be very suspicious about this because, well, quantum theory or quantum computing in general, in 30 years' time, I mean, we've got like something like SCHULD's algorithm, but in 30 years' time, we don't have a quantum algorithm where we can say it's exponentially faster and we can prove it. There's always these conditions, or there's a couple of like assumptions that you make, and maybe that's just how science works, right? So this meta is extremely hard, and let's put it like this: the question you ask here is like the same as, are there breakthroughs in the question on, are classical machine learning models, is this model better than another one? There will always be trends, and like there will be little like increments in understanding. Yeah, but this big paper of like, we know now that quantum machine learning is much better, this hasn't happened, and I don't think this will happen, and I think this would be dodgy if it happened, actually.
And for someone interested in starting, so doing quantum machine learning, but if the person doesn't have access to a quantum computer, are there simulators that the person can use that use GPUs, or what is available for
the
normal person?
Yeah, thousands and thousands. So first of all, you've got access to quantum computers. If you just look at what's in the cloud, so a couple of startups and companies, often actually probably like in a couple of months' time, there will be more than there are now today, because it's like really quickly growing. But you can, for example, go to the IBM Quantum Experience homepage. So I think everyone gets access there to a quantum computer. A lot of other companies give you access when you say you've got a research project, so you just have to like get in touch with them. But yes, there are also lots of simulators, and literally just Google quantum software. I think you find probably 100 different languages and a lot of packages. In quantum machine learning, it's a bit rarer, and I think we discussed yesterday already. So there's Penny Lane, the one that I was talking about. If you are sold on TensorFlow, maybe you should try TensorFlow Quantum. And this also comes with its own like simulator, basically written in TensorFlow. Qiskit is the language of IBM. Forest is the language of, or the software framework of Rigetti. So every company basically has their own simulator software, their own, well, computational framework, and their own language, and their own resources, their own community. So it's actually the other way around. The problem is there's too many probably of them at the moment.
And so by now we have implementations or concept from machine learning into quantum machine learning, for example, quantum SVM. So is it possible to use quantum SVM in one of these simulators? And can we see already results? And what are these results? Similar to the existing ones in normal computers? Better, worse?
Yeah, so almost every quantum machine learning paper exactly answers those questions for a particular model. So they will always like take a model, and then they will take a very small data set, or they will take MNIST and dump it down to 8 dimensions or something with principal component analysis. They will take those like very small dimensional features, put it into, simulate the quantum algorithm. Then they train it and test it and whatever. Then they run a neural network that kind of they think compares to their quantum circuit. So for example, maybe if the quantum algorithm has 2 qubits, you would have a neural network that has also like only 2 neurons or whatever like that, or is like 2 layers deep. It's very hard to actually compare the two and say like, okay, this benchmark is fair, this is not. And then they would report exactly like in machine learning papers, which one is better. And obviously almost all papers find that the quantum model is at least good at something. I think this is a complete bias. I think the whole scientific community in quantum machine learning is at the moment trying to show the world that this works, and this is the wrong statement. You should be critically thinking and show the world maybe that it doesn't work as well. But then the questions start: how do you really compare? Like, is this fair? Now, if I have 3 qubits on a noisy device and I run it against a really huge neural network that has been developed for 80 years versus a machine that has been developed for 1 year. So I personally started, I always thought, how do you make these benchmarks to answer exactly your question? And a year ago, something I realized I don't want to do benchmarks anymore. So I refused to like run a quantum computation against a classical one to see if it works or not, because the results are so random. Sometimes something works, sometimes it doesn't. Depends on the data, depends on the size, depends on the comparison. So I'm actually trying to avoid these benchmarks and try to first understand what is actually happening here, and then we can go the next step.
convolutional neural networks are very popular to process images. What would be an analog of convolutional neural networks in quantum computing? Is there one?
Yeah, of course, there's convolution. So you find everything in quantum is always has a Q, and then you take the classical concept and make a Q, and then, yeah, so there is a couple of papers. So I think there was a Nature Communications paper on quantum convolutional neural network. There are different ideas again. So every time you hear the word quantum neural network, people are referring to this trainable circuit that I was just talking about. I don't know why everyone calls it quantum neural network. So as I said, for me, it's an SVM, it's not a neural network. But yeah, and the ideas are often to do a hybrid strategy. For example, you feed in, you do a classical convolution. So you kind of have this pooling layer, and then the output of this pooling layer you can feed into the quantum computer. So you can like create these hybrid models. You can invent your own one. There's probably a clever way of how to do a convolution on a quantum computer as well. Whether it's good or not is always like a different question. And then lastly, if you go to pennylane.ai, there is actually a homepage where you find a lot of demos, and there's definitely also a demonstration or tutorial on quantum convolutional neural networks, so you can actually read up on it and implement it yourself quite easily there.
Is there a connection between quantum embedding and random matrix projection or reservoir computing, such as echo state networks?
Yes, I know too little about this. So I researched on this like a couple of years back, but I know too little about this to answer this. I have seen these concepts in quantum machine learning a few years back popping up a lot. So for example, reservoir computing, you can just imagine, it's a very physical concept, right? Like you can imagine to have kind of like your quantum system, and then there's kind of like a heat reservoir. This is like what physicists take a lot, or just like a couple of like unobserved states or something like that, or systems. And so people have walked in that direction. I think there's hardly anything in classical machine learning where you don't find a paper where someone has proposed to do this in quantum machine learning. It's just, as I said, I don't know if this is the right way, because then you propose it and no one knows if it's good for anything. So yeah, but just check it out. Just put quantum in front of something, and then you will find probably the paper for it.
You have mentioned quantum data. Could you please explain what is it? Is it the result of experiments in physics or something else?
Yes, so that was the question of yesterday, and it's completely right. I don't even know that I tried not to mention quantum data because it's so confusing as a term, and I seem to have done it anyways. So there's two definitions of it, and people use it completely, ridiculously random. I mean, people have to really explain what they mean by it when they use it. So one is exactly that, what you're saying. So it's the very classical data, basically stored in a classical computer. That's the result of quantum experiments in the lab. So there's nothing really quantum about the data, except from that it comes from a quantum experiment. So the data will kind of be able to exhibit like these non-classical correlation structures. So we were able to trace it in the data, but they don't inherently, have a quantum property, that data. And the other use is to talk about quantum data in terms of, you really have a quantum system in a certain state, and that state carries information, and information and data you can always link together. So then quantum data will be, really like the preparation of a certain quantum state in some sense. And this is interesting. I think I mentioned this because you could now take a quantum computer and act on this physical system in some sense. So for example, you have a photon that carries information, you feed it into a photonic quantum computer, and then you start analyzing the photon itself instead of measuring, having classical data, then feeding it into a new quantum machine learning algorithm, and then working with this. And some people say that that idea, although it's very futuristic, might one day be the one where quantum machine learning is really good at. So that you've got fiber optics everywhere. You don't even have to measure what your photons say and put it into a classical computer, but you literally just feed it into a quantum computer.
And if circuits have physical realizations, how could they be changed during the learning procedure?
So the idea of how a circuit kind of in the lab happens, I mean, okay, it's more a comic or a caricature, but like you can really imagine you have, a box that's your quantum computer, and let's imagine like maybe 100 or 200 years ago, you had like really knobs that you turn to change the properties of your system to act on your physical system. And so how training would be done then is like literally you run your algorithm or your quantum algorithm forward. You remember you have to run it forward in a certain minute 2 times. You do some classical post-processing, you get a gradient out. Then a classical algorithm computes how do you have to update your parameters. It's very straightforward. And then you kind of know what's the new setting of my knobs, basically, to implement those parameters that are new for the second round. So it happens really like in classical machine learning, only that in the end, that your computer, when it runs the model, sends information to some kind of physical setup, and things are changed. But these physical setups obviously get smaller and smaller and smaller. At some stage, there will be chips and everything looks like a classical computer anyways, right? So in some sense, it's maybe a little bit like in a classical computer, because what you do as well is you have a physical state of bits, right? And what does machine learning do? It computes parameters that change the bits in some sense. And it's actually not so different from quantum computing in that sense.
And quantum machine learning seems to be a field where one needs a lot of background knowledge in multiple areas, such as physics and computing and so on. So what can be done to make this more approachable to a broader audience?
Yeah, that's the big question that everyone has, because quantum computing is really looking for talent and for people, because in industry has grown so quickly in the last years that there are not enough basically very well qualified people who want to work in industry. And so that what happened from there is that a lot of, for example, when people do open source software, or when companies put out like learning frameworks, that they actually put quite a focus on community development and making it easier for people to access that material. And I would say 5 years ago, it was almost impossible to understand quantum computing if you didn't have a physical background. I mean, there is a really nice book on quantum computing called from Nielsen and Chuang. It's our big Bible. I mean, I think it's the most cited physics book of all times in all disciplines. And it's so well written and so nice that probably even a non-physicist can actually walk the first steps with it. But 5 years ago, other than that, it was a very physical type of discipline. And I think nowadays people really approach it from a different way. And there are a lot of learning materials out there where you just, with a bit of linear algebra and the knowledge of bits, you can get yourself really far. And also we need those angles of people who don't see the physics anymore, because this physics part will get less and less abstract. Like in your normal computer, you don't have to be a physicist to use a computer anymore. And this will slowly happen there as well. And increasingly, we really need machine learning people, and we need really, I would really love if quantum machine learning would get a lot more talent from people who think about machine learning on a very theoretical level. So people who understand generalization bounds, who understand capacity measures, who know kind of what the theoretical problem of machine learning looks like. And if they would come and inspire us to be a bit less naive maybe on how we approach things, that would be fantastic. So I don't know if I drifted a bit, but so I think nowadays you should find enough material that everyone can read.
That's great. And related to this is basically, which research questions in quantum machine learning research do you find interesting at the moment?
So I'm super crazy about these feature maps. And for example, so this is now very biased, obviously. I really want to link or make a link to kernel theory that's a bit more solid, to really explore the question, what reproducing kernel feature, what feature spaces, let's put it like that, quantum computers can access, and what's different about them. And is there any feature map or any kernel that a quantum computer can implement that's difficult on a classical computer, for example? And then the second big thing for me, so I'm looking at it very much from a theory perspective, is really to say something about generalization power of quantum circuits. So this is something we have hardly touched. We know something about the expressive power, we know how to optimize, but you should be able to say something about how well can a quantum model generalize. There's almost nothing out there
yet. Someone is asking about the actual name of the book. So this introduction to quantum computing.
Oh, okay. It's called, I can write it down in the chat just now. It's called
Please.
Quantum Information and Quantum Computation, I think. Nielsen and Chuang. And I think you will find it immediately. Do you even have a link? Okay, cool. I'll check in the chat and post like a link to some official version. Yeah, I think every university library has it. Yeah. And there, by the way, if someone wants to learn more, so we've got a book as well that I co-authored, It's kind of the first edition that came out a couple of years ago where things weren't so clear yet. So the second edition will come soon. But if you want a copy or an e-copy of that, then you can also just inbox me, or I think you find my email online, but otherwise just inbox to maria@xanadu.ai. I think I've got it. No, I don't have it here, but you find me like through those channels.
So in your opinion, how far are we from quantum computing being commercially available to the masses?
Well, it is commercially available in the sense that it is available. I mean, you can run an algorithm on a quantum computer in the cloud. Everyone can do that. It is commercial in some sense. So like, for example, I work for Xanadu, which is a startup that builds photonic quantum computers, and we have like commercial partnerships, so where we get paid for our quantum computation. And so in that sense, it's already there. But if you think about, the idea of that banks use it, or that, like that almost every company has a quantum computer or buys access to a quantum computer. Yeah, how many years? I mean, scientists always say it's 10 years if they kind of don't believe it happens immediately, and they usually say it's 5 years if they're kind of about to do it. So I would say 10 years, but it's probably more like 20. But again, there's a grading, right? There's a scaling who uses these devices. And in the idea of how, for example, like emerging technologies work is there are always these early adopters, and they already use these devices commercially. And then there's this like mainstream idea of people using the technology. And I think it depends really very much on what level are you talking about.
Mm-hmm. And as our last question, can you please share with us how you got started into quantum computing and quantum machine learning?
Yes. Yeah, I'm maybe not the typical person to ask here, because I was always interested in physics, maybe more from a philosophical perspective, or I just wanted to like know these things. That was something that I thought it was fun. I had very bad physics classes in school though. And then when it was time to study, I kind of walked through the physics department in Berlin. I think it was at the Technical University. It's a very dark space, and I kind of decided not to study physics. So I went and studied political science and actually finished that degree. But in the meantime, I was kind of like, I should have done physics actually as well. And then I did both for a long time. And then I somehow came to South Africa. And then after, basically I had a master's degree in physics and in political science, but I always wanted to work in political science because I thought like, physics, I don't fit here, and this whole like science, everyone's nerdy. No, I'm joking. But like, I was just like not feeling entirely like myself there. And so I went for a couple of job interviews and I didn't get a position here in South Africa in political science. And then I decided to do a PhD in physics just to look what happens. And now that was actually the point for me, probably the best decision of my life, because what happened was I was super free because I didn't want to become a physicist. I didn't want to stay in science, to pick a very crazy topic. And quantum machine learning back then was in 2013, wasn't even a term yet. I think you couldn't even Google it. And so just by like being free to choose whatever I wanted, I kind of had a PhD where I kind of could be part of a field developing really, and be part of the very, very early community, sit on the first conferences ever with the first people who thought about this. And yeah, it's opened up so many opportunities. So yeah, I think I was a bit, kind of coming from lots of like ways and then just wanting to do something that's very crazy. And now it's something that's actually quite real for me. So yeah.
Well, it's a very interesting background, so political science, physics, and now quantum machine learning. So it's very exciting here. And with this, we could finalize our session for today. Thank you very much, Maria. So it was something quite different to what we have seen over the past days, but still very exciting. And I am sure that participants might have more questions. Probably they will contact you by email. And otherwise, thank you very much for being part of the school.
Great. Thanks for having me. Bye, everyone.
Have a nice day. Bye.